This is the solution video for question 4 of the modules of Moore circle of 3D stress and static failure theory. In this question, we have been provided with a shaft that has the solid segment at A to B and a hollow segment from B to C, which are rigidly joined by the coupling at B. If the shaft is made out of A36 steel, we need to determine the maximum torque, which can be applied according to the maximum distortion energy theory. We're going to use a factor of safety of 1.5 against the yielding, and the yielding stress has been provided for the A36 steel as 250 megapascals. So first of all, we're going to note down what we've been given. We have the yield stress as 250. A factor of safety as 1.5. We also have been given a radius for the different segments. So I'm going to call my radius for the solid segment as RS, which is just our 80 divided by 2, 40 millimeters. If we want to use meters, it's going to be 0.04. Then I have the hollow section, which is going to have an inner and outer diameter. So I'm going to call this radius outer hollow as 100 divided by 2, which gives me 50 millimeters. Or 0.05 meters. And then the inner diameter for the hollow part, simply radius inner hollow, just the same as for the solid, so it's going to be 40 millimeters, or 0.04 meters. So the first step that we want to do is to determine which part is the most critical part. So it's going to be the hollow or the solid. Before we start doing the calculations, I'm just going to draw like a little easy free body diagram. So I have my solid section here, my coupling at B, and then I have my hollow section out here. So again, my point A, my point B, and my point C. And I'm going to have an unknown torque acting on this element as such. And what I want to do, I want to determine the critical section I'm going to start with my solids, so segment AB. Solid. And because I only have a torque, I know that I'm only going to have a shear stress. So my shear stress, and I want to look at the maximum shear stress in AB. So I have my torque times the radius divided by my rotational moment of inertia of the cross section. So the cross section in this case would then just be a circle. So I'm going to put my T in this blue color. My T is my unknown times my radius of the solid, which is 0.04, divided by pi on 2 times my radius to the power of 4. If I put that in my calculator, I'll find that my radius will be 9,947.18 to the unknown torque. And when I write this out, because I'm doing it in my unknown torque, this is only in pascals. So note how I used my my meters rather than millimeters. We want to recall that this is in pascals so we don't get confused later on. Then we want to investigate our hollow segment. So this segment BC, hollow. So my maximum shear stress BC is my torque times the radius. But just recall that this is a hollow cross-section, so my cross-section, although it's still a circle, we need to deduct for our rotational moment of inertia, we need to deduct the inner part. So just be wary of that when you do the calculation. I'm just going to sketch this out and recall that our hollow part, we just have this kind of pipe looking thing, right? So the only material we have to deal with is the material in here. So for the calculation of shear, in this one, we are simply doing the whole radius. So we are just looking at the outer hollow. We're going to divide it by our rotational moment of inertia. I'm going to write it out separately. So again, my torque times radius of the complete circle. And then my rotational moment of inertia, that's when we look at simply just the material section. So pi on 2. And then we have our radius outer, the hollow section, to the power of 4 minus our inner radius of the hollow section to the power of 4. That's how we would calculate that. So again, we put in the values. I'm going to put my t as the unknown times 0.05 divided by pi on 2, 0.05 to the power of 4 minus 0.04 to the power of 4. We put that in our calculators, we'll get 8,626.2. And again, T, which is our unknown torque. And again, this is in Pascal. So if you put this straight in your calculator, you'll end up with a very tiny number if we were to do it in terms of megapascals. So we'll keep that in pascals. All right, so how do we then determine the critical segment? Well, our maximum shear force in AB is larger than the maximum shear force in BC, which means that the critical part would be in our AB section. And the reason for this is when we then put our torque value in here, in our hollow section, if we put, say we found that it's 1,000 or 100, whatever you will find later on, and we'll put that in our AB and BC calculation, what you'll find in the shear stress for our AB segment, this will be a lot larger, which means that's where it will fail quicker, if you want to call it that. That's the critical section. So if we need a lower torque to be within that limit, rather than if we used it for the segment BC. All right, so now we want to find our torque, and that's our step 2. We're going to find our torque from our maximum dissertation energy theory. So I'm just going to shorten that in here. Sorry, max distortion theory of energy. This is when you can blame English as the second language. All right, so because we know that our shaft is subjected to pure shear, so pure shear, we can then define our principal stress 1 will be equal to our principal stress 2, negative principal stress 2, which is the same as our shear stress, right? So that's only for our pure shear stress scenarios. There we go. And in our case, that would mean all these will be equal to shear stress max in AB. And these will then apply to the maximum distortion energy theory. And the equation for that is simply our principal stress 1 squared plus our principal stress 2 squared minus principal stress 1 times principal stress 2, which will be equal to our allowable stress squared. So the first thing we want to do, we want to find this allowable allowable stress, and we will find that from our yield stress that we were provided and the factor of safety. So it's simply just our yield divided by factor of safety. So 250 divided by 1.5, which is 166.67 ish megapascals. So now that we know the allowable stress, and we know that we're going to replace all these ones with our maximum shear stress in AB, it's just a matter of writing it all out. So my first part will be 9,947.18. And remember, I have this unknown P to the power of 2. And because I'm doing this on my computer, I can simply just copy this. And then I know for the second part, I'm just going to add the same thing again. Squared. And just remember negative principal stress 2. So we're going to have to put a negative sign in there. Minus our principal stress 1 times our principal stress 2, which again don't forget we need to add that negative sign in there, minus, which will be equal to our allowable stress. So 166.67. Just remember, this is in megapascals, whilst previously we said this is just in pascals. So it will be 10 to the power of 6 in order to get them all in the same unit, and then squared. What we'll do, we'll rearrange all this and put it in terms of our T. So that way we can solve for our torque. And our torque will then be 9,673.6 Newton meters. Or we can say 9.67 kilonewton meters. And that is it for this question.